Hoje ela acho que está na UF para a banca do doutorado, essas coisas. Por isso eu vou fazer uma coisa primeiramente eu queria fazer obter propagador para gluon em diferentes gauges, mas qual é o comportamento deles em ultravioleta e infravermelha, mas depois eu pensei que ela está fazendo muito boa coisa, né? Porque ruim dá. Porque ele está, por isso eu não vou fazer isso porque é difícil para match his abilities. Por isso eu vou fazer uma coisa mais diferente. Ok, tudo bom. Eu queria fazer um curso com este assunto, mas este curso começou mais tarde, por isso eu não posso vir. Agora, quando eu tenho tempo, eu vou dar poucas palestras sobre isso. Tudo bom. Hoje, eu vou só dar uma introdução. Qual é este assunto? Não? Eu vou dar motivação, mas eu não vou fazer muitas coisas hoje. Tudo bom. Tem boas. Este é um assunto física do século XXI. O que significa isso? Antes que isso tem aqui eu dei uma lista de referências para isso. Né? Primeiro foi Grassmann in Geometry and Sketching Amplitudes, do Neymar Kanyama e outras pessoas. Erlang Huang, Sketching Amplitudes in Gravity and Gauge Theory. Essas coisas. Tudo bom, vocês já têm isso, né? Eles olha para datas, eles são muitos recentemente, tudo bom, referências. Vocês conhecem este símbolo, né? Porque muitos... sim. 2015. 4 livros. De tudo, isso foi em 2014. 2014, 2015, 2016. Muito novo. Este área é muito novo. Por isso, eu só esta, por assim dizer, testando água. And testing waters. Aqui, história começou tudo. Em 2003.
Você falar bem, fale inglês, porque isso aqui está sendo filmado.
Sim.
E daí passa para português.
Sim. E melhor falar em inglês?
Olha, não sei se não sei se é isso. Isso aqui está sendo filmado. Se ele falar bem, o filme passa para o inglês, para chinês, se quiser. Entende? Então,
se é o que ele sente melhor, dá certo.
porque eu acho que
melhor em português,
Pode falar em inglês.
In English? Okay.
Para mim, tudo faz.
Tudo bom? Hey, tudo bom? Okay, perfect, very good. Okay, so now I have so much of, there will be very less head eating, right? So because I'll be constantly in real time translating in my head from English to Portuguese. So, this is perfect. But if it's a basic course, of course, like I'm going to write in Portuguese and then speak in Portuguese. But this is quite advanced, right? I think it's so advanced. I don't think it's a formal course in any university anywhere in the world. Right? So people do teach this kind of things in summer schools, winter schools, like special schools, but not as a formal course. Right? So because it's so advanced. See, all the textbooks are so recent, 2014 and 15. Very good. So thanks for the freedom. Okay, so the story started in 2003. Ed Witten showed in something called twistor string theory, right? So in twistor string theory. In twistor string theory, he showed in twistor space if you calculate in twistor space, if you calculate the correlation functions, this is in twistor space, calculate the correlation function. This will give you in space-time it gives you scattering amplitudes. So if you're calculating correlation functions in twistor space, it gives you scattering amplitudes in space-time. This was very strange. Nobody expected this kind of behavior. So this was in 2003. So later, these ideas have been generalized to find the scattering amplitudes in superangles. Or sometimes they just say QCD, but it's superangles. Okay, so, and also in supergravity. Sometimes they just say gravity. Right? This is the whole thing. In order to understand this, you have to know many things. One is twistor theory. which was introduced in the 1960s by Roger Penrose. Then super animals. This is basically n equal to 4 super animals. Yes. And this is n equal to h supergravity. These things, right? So why I said this is the physics of 21st century, because all the results, everything was discovered in this century. Everything is new, right? So this is the thing. Guess what? I will not be doing any of these things today, okay? Because this is too advanced, right? So this is the original plan. So next, when I get the chance, I will talk about other methods of calculating the scattering amplitudes, and then maybe one such lecture, crystal space, one such lectures, super animals, and then n equal to h supergravity, then these things, right? So I think this is a very, very hot area of research. Not many people do this in Brazil. Actually, I don't know anybody who works in this in Brazil. So, except, for example, the crystal space, that's been used by Nathan Berkowitz in São Paulo. He has something called pure spinor formalism. It's like an alternative, let's say, approach to string theory, but that's not necessarily this, right? And there is another Pedro Vireira. He works in Perimeter Institute and ICTP, I guess. He has done some works related to this, but I don't know anybody who has worked with scattering amplitudes in this kind of approach, right? So that's why am I following Hillel around is because if there is anybody who can start a new group on this kind of thing, I think it's only Hillel who can do this, because he knows both super animals and supergravity, and then he's open to new ideas, right? So if anybody wants to like do a project on these things, like doctoral project or master's project, we can talk, right? So I'm just looking for somebody. Why am I giving this? This is because to find somebody to just talk about these ideas, right? So far I failed to find anybody who would listen to me. So that's why I had to force you to this thing. And also, look here. I have a tradition. What is the tradition? Like, look here. Finding mistakes, right? So in what I say, if you find any mistake, if I write anything wrong, like any typo, there is a square, I miss the minus sign or something. If you find any mistake, you get a try. So, and if you ask any questions, you get this. Okay. So, because I want this to be like more of a discussion, rather I will be giving a talk and you will be listening, because you could be thinking about anything, right? So I am doing this for my sake, so that I want you to ask me questions, and any question, any simple questions, anything. Don't worry about that. Ask me any question, I'll give you a talk. Okay. So this is the idea. So far, any questions so far? This is it. So what is the purpose of me giving lectures on this topic? Is to understand, to make sense of this, right? So if there are any new papers on this, you should be able to understand or find mistakes in those papers. So what's happening? This is the whole idea. But for today, I will not be doing this. I will be giving motivation about why we should be studying gauge theories and gravity together, and then why we should be studying scattering amplitudes, right? So that's all I'm going to do today. So none of this stuff I'm going to do. So far, any questions so far?
I will make one.
Please.
I personally, I don't believe in the physics of 21st century is something connected with superstring, gravity, or things like that. I don't believe it.
Sure.
This is some history that the people in America invented. They don't know how far you are on that.
Sure.
But what I believe?
Yes.
I believe that nowadays people are moving the electromagnetism from electric charge to photonics. And people around the world, they are organizing lasers for measure photon-photon interaction.
Exactly.
So photon-photon interaction is something it's the physics of the moment.
Exactly.
I don't believe it's
Sure. Yes.
this is physics, but
Sure.
not this. So the people they want to know how the photon interacts with the photon. I think why we are in 1923. At that time, the people discover the photon has particle
Sure.
because the interaction with the electron.
Compton is- Compton,
Reacted. And then they say, oh, we have a new particle
Sure.
that photon not has radiation but has particle.
Yes.
Now they wanted to understand how the photon, for example, all the LHC, everything is photon-photon interaction generate another particle.
Sure. Yes.
So LHC and lasers in Russia, in US,
Yes.
in China, in
Everywhere. Yes.
France, Italy, they are on that. So I think that would be nice in your course, that is, let's see,
Yes.
scattering amplitude,
Yes.
to also to include photon interaction.
Sure.
Well,
Yes.
prior to this supersymmetry, things like that.
Yes. Yes. Continue, please. Yes.
So, for instance, we have you can have photon interaction through QED or through non-linear electromagnetism, no?
Yes.
So this will be something very good for us and
Understand this. Okay.
I think the text is good to speak about the twisted string theory.
Yes.
But here, no.
No. Okay.
You are going to lose your time.
So, did you? I think I had some list of these things, but did you guys follow the argument? The argument is okay. So sure. But by the way, how many of you have studied any type of scattering amplitude already in quantum field theory course? Like, have you studied any of the scattering amplitude? Have you calculated like 3-level diagrams and one loop? Right? Okay. So so far, so the professor is saying there is no experimental evidence for any of the supersymmetry things and other things. So he says, why should we do this? This is voodoo physics, right? So like voodoo, do you understand what voodoo physics is? Voodoo is some sort of a black magic. Right? So black magic physics, sure, yeah, you can say anything you want, you're entitled to your opinion. The other day, Hillel gave 2 reasons why supersymmetry, right? My one purpose of this course is to give another reason why supersymmetry, maybe 2 more reasons. For example, I will show you as we go along, right? So you don't have to believe in any of these things, right? So you can also make a you know, in protest they make these plaques, the signboards. You can also make a signboard saying that why should I listen to you when I can stay at home and then watch Netflix? You can always show me that like this. Okay, so I'm going to give you a reason why. Okay, so one of the reasons the way I want to look at supersymmetry or these ideas is something like why we study, like in elementary physics, why do we study frictionless air? When you study the projectile motion, there is no air drag. But there is air, why do we study that? Right? Maybe you can say, oh, when we go to the moon, maybe there is none. Or when we study things, point particles, are there any point particles? No. We study things without any friction. Because that makes things easier, and then we get an idea, and then you make it more complicated and more realistic, and that becomes a real world problem, right? So the way I look at supersymmetry is something like this. Why do we study supersymmetry? Although there is no experimental evidence for this as of now, but any of the experiments in LHC or elsewhere, there is no evidence. Why do we study this? Because it makes things a lot easier, right? A lot easier. For example, that's what today I'm going to give you this. What's the purpose of today is why do we need to study these things, right? So For example, QCD is a theory of real world, right? So if you want to calculate the scattering amplitudes for this thing, for example, one of the most famous backgrounds in LHC, I think I'll talk about this things more later. People did not calculate those simple processes. Quark and a gluon come together and then go. Quark gluon, right? So it's a simple process, happens in any of the hadron colliders. Nobody calculated the one loop amplitude of this process, quark gluon coming and going, until 1990. Until 1990. That was what, like 30 years ago? Less than 30 years ago. Nobody calculated this. If you want to calculate certain amplitudes, let's say 3 loop or 4 loop amplitudes, they're called, for example, so the scattering amplitude, right? So amplitude is usually written as like mean. The whole process, you can write this as like mu 0 plus some coupling constant, right? So Halal is using the same notation. Mu 1 plus g squared, mu 2 plus g cubed, mu 3, and so on, right? So this first term, when the coupling constant is weak, we can write the amplitude like this. So if your experiment is not very precise, it's good enough if you calculate this. Later I'm going to demonstrate for the magnetic dipole moment of the electron how these things are calculated. Right? So this thing is called tree-level array. This is one loop, 2 loop, 3 loop, right? So, and that's numbers about the precisions they give. Usually, yeah, this is what in quantum field theory we call them as tree loop, tree, 1 loop, 2 loop, and questions. This. Usually in particle physics, the phenomenologists call this leading order, right? And this says next to leading order, this says next to next leading order, and this says next to next to next leading order, right? So just N3 or low, right? So these are the questions. For most, so all the physics until like a Tevatron was at the Fermilab, right? So now people say we have entered the precision era in particle physics with the LHC. What do they mean by that? So that means they're calculating for the processes next to next leading order and then more than this. Two loop is the state of the art, right? So next to next leading order. And then if you have this, the uncertainties, right? So here, the uncertainty in your calculation is about of the order of 1. And here, this is 10 to 20%. Here it's 1 to 5%. And this is less than 1%. So less than 1%. So if you calculate for the same process, let's say gluon coming and then they scatter and then give another gluon. This is the thing. This is the accuracy of the perturbation order. So right now, before LHC, we were here like 10 to 20%. So that means this is the uncertainty. If there is any new physics, what are the new physics we are looking for? Yes. So that can be hiding here, right? So that can be hiding here. So this is why we have to calculate higher loop level amplitudes, right? And these methods, oh, okay. So why am I saying this? In order to calculate this, for example, I'm going to show you this. Make a table of the number of, I will make a table of, this is the number of gluons, right? N gluons. I think I need a bigger space than this. So let me.
Do you have experience to make an amplitude calculation with computer?
No, but there are programs available for these things. Some of them are not available in public. There is something called FailCalc on Mathematica we can use. And there are some online things. They're used for gluon calculations and LHC. But if you want for the photon processors and this kind of things, we will have to write this. Just to demonstrate
Do
this.
you have experience? Do you have experience with making this calculation with computers or?
No, I haven't done this with the thing, but we can do it. I'm going to write like n gluons, meaning like let's say one. Right. So it could be like 2 gluons come and then 3 gluons go out, right? So this is something happens here. It's a 5 gluon process, right? So how do we calculate this to tree level and this kind of things? So let's say if there are n gluons involved in this kind of a process, let's start with a minimum of 4, right? So n gluons. And then this is number of Feynman diagrams. This number this means number, right? Not hashtag Feynman. So maybe I knew like Feynman was here. In fact, the only few things that I knew about Brazil before coming to was by reading was what I knew from reading Feynman's Surely Mr. Feynman. I don't know if Feynman was ever in this room or not. I don't know how new this building is, but anyway, so this is not hashtag Feynman, right? Okay, so this is number of Feynman diagrams. Number of tree diagrams, right? So tree level diagrams. I'm going to write this to you. So that's fine. Okay, so if this is 4, right? So if there are 4 gluons, then the number of tree level diagrams, the Feynman diagrams, is 4. So you can write those 4 Feynman diagrams. There are roots, and then you can calculate the amplitude. It's good. This can be given as a homework problem in QCD, right? So, and if there are 5, you are going to have 25 Feynman diagrams. This can be given as a homework problem to you if your professor does not like you, right? So this is. Otherwise, nobody gives this as a homework problem. So if there are 6 gluons, you are going to have 220 diagrams. And if there are 7, you are going to have 2,485. And for 8, you're going to have 34,300 diagrams. If you have 9, 559 and 405. Those many diagrams. And if it's 10, you have more than 1 million. See, usually you put the thing, right? Sorry, it's 10 million. But here, the comma and full stop, I'm just afraid that we get confused with my. You're not getting confused with this. It's not 10 point something. This is 10 million something. So this is 500,000, 34,000, 2,000, right? So diagrams. And all these diagrams are relevant if you want to calculate at LHC just glue-on processes at the tree level. This is only at the tree level, right? So number of tree level is this. If you want to go to one loop, the number is going to be different. I have only one of the things for one loop. For let's say 7, because it's one of the important processes. For 7, this is 227,585. Only for the 7. I can find and then fill this table for other processes. This is one of the important processes, one of the important background processes for LHC. This is this, right? So, nobody can do this. Computers cannot do this. Why do we have to do this in the first place, right? So this is only tree level things. So tree level is here. So if there is anything new physics, extra dimensions, supersymmetry, whatever new voodoo, black magic is there, if you want to see that, it's going to be hidden in the signal. It's definitely not big enough, right? Otherwise we would have discovered this, right? If any of these effects are big, let's say tomorrow you find a new theory which says there is an elephant in this room. That's not correct because there is no elephant, right? But if you find, if your theory says that there is a bacteria in this room, an alien bacteria, you could be right, maybe, right? So it could be anywhere. It's hidden. So we should have a technique enough to go look for places where we can eliminate, oh, there's no dog in this room, right? So we have to see and eliminate things. There is no fly, there is no mosquito, there is no bacteria in this room. So you need a more and more precise calculation. So that's why for LHC, if you want to discover anything new, we have to know the old physics to high precision. Right? So this is the slogan. Let me write this. In order to discover new physics, we should know the old physics.
Not so much.
To very high precision. Not so much. Why? If there is anything, like if there are extra dimensions, supersymmetry, right? So these are the two favorite candidates for popular press to write about, right? So that everybody knows this thing. They are definitely not big enough to be found. So you have to, they could be hiding in 1% error. If you are not sure of your standard model calculations, 1%, how can you find something which is 100%? No, right? So for that you have to calculate, you have to know your old physics to a very high precision. This is called precision physics, right? So that's what we have been doing with standard model. Why we could not discover
I will ask you so. For instance, in the 50s, the people understood in very high precision on QED.
What was the precision?
What?
What was the precision in the 1950s for the QED?
But the point is the following. Nowadays, there are nearly 50 models trying to go beyond Maxwell equations. If QED is the final theory, why should we go beyond Maxwell equations? I'm saying, I understand what you're saying, that you have to understand one theory to go to another.
Oh, but this is not true statement. In the 1950s, the professor is saying in the 1950s people knew QED to very high precision. that precision was one loop that was calculated by Schwinger. Okay, so people did not know to a very high precision. So in 1928, Dirac, for the first time, showed the magnetic dipole moment of the electron should be 2, right? So and experimentally they found it's approximately 2. That was 1928. But it was approximately 2. Dirac would not be very happy with something approximately 2. If you want to know more about this, talk to Hilaire. Right? So, he can talk about this for like 10 hours. That was 1928. So since there was a discrepancy between the experimentally measured value, which was approximately 2, but not exactly equal to 2, Dirac calculated this to be exactly equal to 2. Right? So people call this, what do you call when your experiment does not agree with the God, who is Dirac in this case, right? So you would call that as anomalous. They're not saying Dirac's theory is not complete. We need a new theory, better theory of electron and positron. They're saying the experimental result is anomalous because it's not exactly agreeing with the Dirac's theory. So it was in 1948, Schwinger calculated one loop correction to this, and he showed, later I'm going to give you the list of all the calculations, why the precision is required, right? So he showed with one loop, and his experimental value agreed with the theoretical value. Maybe this is the right time I show you that, right? So this is the right time I show you that. So definitely we need to know to very high precision than this. And in the 1950s, people knew almost you know better physics today about quantum field theory than people in the 1950s, including Feynman, Tominaga, Schwinger. You know more than they did back then. So you are better than them. So you're better than them. That's the whole point of being in a new generation of physicists, right? So what I want to do is, like, one of the purpose, like why I want to put these things together is to change this kind of attitude in physics. We are a new generation of physicists, right? So there were like old generation people. They would study general relativity and then study cosmology for the rest of their life. They don't know anything about one loop corrections in QED. Same thing in field theory. They would study quantum field theory, then go do particle physics, and they don't know anything about Schwarzschild metric, let's say, okay? But the problem that we are facing today, if any of this approach would be good enough, people would have solved all the problems today. We would be just doing something else, not thinking about the problems. Like, what are the problems? Dark matter, right? Baryon asymmetry. They are more like particle physics problems, but they are also cosmology problems. Well, I will go into that later, right? So now, since I am in a good mood to show how calculating the magnetic dipole moment of the electron has changed over the years, and you'll be surprised to know.
I'm going to ask you.
Go ahead.
This sentence that you wrote here.
Yes.
For instance, I think the challenge nowadays is photon-photon interaction.
Sure.
At 3 levels.
Sure.
3 levels. Okay?
Sure.
So all the things, string, supersymmetry, the thing for me doesn't matter. Okay?
Sure, definitely.
For me, it matters a lot if you have any model that shows photon-photon interaction.
Sure.
Then the sentence that you are writing down there, you say, okay, photon-photon interaction, what's that? QED is precise. So, photon-photon interaction through QED. This means one loop, not a 3 level. So, I'd say, no, you are wrong.
Sure.
I think, no?
Yes. I think the professor requires both one this and one this. But you continue, yes. Go ahead.
No,
Don't say you're diabetic.
because then, the people here,
Yes.
I'm older, just.
No, yeah.
People here should not be naive.
Sure, yeah, definitely.
This is the point. We are not here, we are in a discussion.
Sure, yes.
So the discussion that I'm saying, that is, let's say, may I go into black?
Please,
Just a minute, just a minute.
There should be fights.
Nowadays, this photo, going, photo.
Yes.
This is the great scattering.
Sure. Yes.
The great scattering. So what happened with this?
Yes.
How to make this? What's the theory behind?
Yes.
And so people did it in the past, this experience. Photo, electron plus, electron minus, wave, photon. Okay? And they are trying also to do this. This is difficult to do this experimentally, this thing. Okay? So these are two big interrogations for physics. So what happens with this? This sentence. This sentence says something. Says that QED is marvelous and simple. So security is marvelous. This photon interaction must be done to QED. Means this. Okay? But this is one group.
Sure, yes.
Okay? So the question is, okay, this is this. So nowadays we have near 50 models beyond max rotation. Different and trying to do something more than this. And the great test is this one. So the people are doing that lasers, LHC is measuring, and people are trying always to say that this is correct. If you want some new physics, you should say, could I have this photon-photon interaction at 3 levels? And then, so you have to discover a theory that photons are interacting with photons.
Yes.
Okay? So, finish. I'm just saying that here is one point very important. We understand quite well what we're saying. But the problem is that we have to follow this or this. Okay?
Yes.
And this is, in my opinion, the most important scattering.
Sure. I agree. Maybe I'll also give you a list of scattering processes which are taught in elementary physics. But here, I agree what you're saying. The reason why there are 50 models still surviving is because there is no experimentally measured cross-section for photon-photon this thing. So when there is no experimentally measured, your theory is as good as my theory, right? So here it's not the problem because QED is good. No, this statement is not saying QED is good. This statement is saying you have to know your experimental decay rates and cross sections, everything, to as high precision as possible, so that if there is anything new, you can find that. If you don't know that, the new physics can be hiding anyway, right? And also, everybody who has taken any course in QED knows this is not the last word. There is something called Landau pole, right? So QED is not the complete theory. There is a Landau pole. That means it's something like having singularities in general relativity. So general relativity is spectacularly experimentally successful. Gravitational waves, 2-3 years ago, Higgs boson, standard model is perfect. We know both of them are not complete, right? So definitely that's why we are going. No, QED is not. And also here, the problem is not with any of the theory or anything. The problem is because of lack of experimental measurement of the photon-photon cross-section, right? So nobody has done, if anybody measures this today in the photon colliders, that's going to kill 95% of the theories. 95% of the theories, right? So there is no number here. So you can produce 10 different theories with 10 different numbers for cross-section. And since nobody has measured this, you can go around with this thing. Here, the problem is not with the theory, not because of our lack of understanding or better understanding of Maxwell's equations of QED. It's purely, naively, simply, we don't have the experimental result for this. So that's why the good lesson to take from here is, if you are a funding agency, build a collider which does this. That's good. That's good for measuring some of the things to high precision, right? So here, it's the problem of experiment, not the theory, right? So that experiment is going to tell all these kind of things. Okay, so since we are here, I wanted to list all the improvements that have been made over the years in the measurement of the magnetic dipole moment, but instead now I'm going to list some scattering processes, right? So some of them, it would be nice if we calculate them to tree level, just tree level, using all the standard textbook methods. Some of the processes, some standard processes, right? So these are number one. It's called molar scattering, right? So this is electron-electron scattering. Second is Baba scattering. By the way, Baba was Indian. He's Indian. He's dead now. He was a student of Fowler and Dirac, right? So he started new research institutes in India, something like CPF in India. So he's very famous. Then Compton is right. So this experiment measured the momentum of the electron, momentum of the photon, and this got him. I think the professor was mentioning this one about proving the photon to be particle with the momentum, right? So this was the experiment. And then Dirac is electron-positron annihilation into photon phase, right? So this is also called paid annihilation. So the other is paid creation. This is, see, with one photon you are creating this, right? So I'm going to, yes, and the last process, I included this just for the sake of the professor, okay? So this is braid below, which is so these are some of the standard processes, standard scattering processes that perhaps one should learn in an elementary course on quantum field theory, basically quantum electrodynamics, and calculate their cross sections, their amplitudes to at least tree level, right? So this would be a good place to go. Yeah. Has anybody calculated the amplitudes for any of these processes? You don't have to, but if you have. Primeiro foi?
Não, é.
Modé?
É, números foram os dois aí. Não, primeiro.
Primeiro, sim. Acho que se vocês fizeram Hazel and Martin, Phenomenology, the quarks and leptons. Se você fez curso em fenomenologia, usando o livro do Hazel and Martin, Quarks and Leptons. Não?
Não, eu fiz lá na UF mesmo.
Ah, tudo bem.
Era quantificadores, ele passou um que era desse aí.
My suggestion for the
Sim,
course
sim.
is sometimes, for example, you don't have time for everything.
Sure, yes.
And sometimes this process,
Yes.
you calculate by you and give notes for us.
Right,
And
yes.
then you publish it in the global teacher.
Sure, yes.
and then the notes that for someone
Yes.
I will be good.
Yes, yes. So these are the processes, right? So it would be a nice experiment to do this. But if I like, see, I want to go to Twister space and super angles and super this thing. This is super far away from that, right? This is the first place we should begin with. Maybe this is a good place to begin, right? So
Because try to understand, your course is going in principle for overview.
yes,
And there are many different people.
yes.
And some people that don't know what is.
No, I totally understand.
And if you create the notes,
Yes.
the people that I know go to the notes, then your course will be formative.
Sure, yes, I understand, yes. So, these are the things, right? So, okay, so maybe I will do this as it is.
Just to remember what you said before.
Yes.
You said you calculate correlation
Function.
function with space,
Yes.
time, scattering amplitude,
Yes.
space time.
Yes.
But you calculate, for example, for young meals here, and you obtain a scattering amplitude of young meals here, or is super young meals, or you obtain QCD? I don't remember.
Very good, okay. So, this is a very good question.
Okay.
It's a very good question, right? So, did you understand what he asked? See, I showed the original bit on this thing. So with twistor space to space time, right? Space time. So which one are you calculating to which one, right? So this was originally shown in something called twistor string theory. So for the twistor string theory, you calculate the correlation functions in the twistor space. The final result, your correlation function will give you for the same theory, for the same twistor string theory, yes, in space-time as an amplitude. So basically, this is something. See, this is duality, right? This is in the heart of the latest revolutions in theoretical physics, right? So not experimental physics. Let's be careful with the professor here, right? So theoretical, this is dual. So it's something like doing in area CFT or gauge gravity duology. So twistor space, but this is a different type of duology. Twistor space to space-time, right? This was the beginning. So basically what Witten did was, he showed whatever the twistor theory was by Roger Penrose, he showed it's part of string theory. So that's all. So that's all they show. You say, oh, we have a non-commutative algebra in physics. Witten shows that it's part of string theory. So that means the whole program is now under the thing. So recently, in 2009, Peter Harava proposed a new theory of gravity, which violates Lorentz invariance. The time derivative is only 2, but it has higher spatial derivatives. And he showed using this one you can construct a theory of gravity which is power countably renormizable. And string theory showed it's just part of string theory, right? So that's what they do. If you say tomorrow if your theory is good, they show it's part of string theory, right? So basically that's what happened here, right? So that's what happened here. But later, using this was in 2003. Later with these postdocs, it's called BCFW. Both Freddy Cachoso, he's from Venezuela, right? He works in Peruvian Institute. Jonathan Fang and Edward Witten. They showed something called recursion relations, and they can be applied to both superangles or QCD, and even to gravity theories. So using these kind of things, you can calculate the amplitudes in both gravity and gauge theories. This is the thing, right? But that was the beginning. Later, this was in 2000. Later I will show you this. In 2013, something called amplitude hedron. Have you heard of this thing? Amplitude hedron, right? So it's a new kind of geometrical structure They show basically all these scattering amplitudes. You are basically finding the area of some thing, some object, some geometrical object in some fancy space. That's all. So this was in 2013 by Nima Ahmed and his student to show this. So I want to like end with this thing with this, like how to make sense of this, like what does this mean? It involves a lot of mathematics, a lot of combinatorics and so many things, algebraic geometry and whatever fancy possible is there in that. Okay? And all this, just to be careful with the thing, these two methods are so far only done for n equal to 4 superannual theories. Right? So can you calculate using this those things for LHC using any of these methods? No. So far, no. So that's why it's a very good area. So people have done some sort of a toy models. I would call any model with supersymmetry as a toy model because it's easy for making the calculation. You can calculate all those things in superangles theory using these methods. If there are 10 gluons in superangles theory, you can calculate using these methods to any order you want. These techniques are so powerful. But is superangles theory a theory of nature? No, because everything in superangles is massless. It's just gluons. I don't think they have quarks in that, right? So it's gluons. So it's not a theory of real this thing. But in this kind of toy model, you can calculate everything using these methods. But that's not the end of it. Like the professor would object this thing. What is this good for? Right? Can we use this to calculate the Wright-Miller process to tree level? No. Any of these processes to tree level? No. Right? So all these methods are applicable only in this kind of toy models in superangles theories. Right? Now it's a problem for us to how do we extend this knowledge to standard model processes. Right? So how do we calculate any of these very down-to-earth real processes? This is Ahosh-Fejal processes, right? So this is real, this is everyday thing, right? So how do we calculate these things using this fancy? Is there anything like an amplitude some object in some fancy space which can calculate these things? No, nobody knows, right? So if we calculate this, if you calculate this, if we collaborate and calculate this thing, that would be a fantastic new progress, right? So, and nobody has done this. Like people are just still playing with the superangles and only this kind of thing, supergravity theories and this. So how do we use this knowledge? Strip out all the supersymmetry. With standard QCD, can we do this? Nobody knows. Right? So in that sense, all this is fancy story. These are fiction. Right? A good high-level, mathematically sophisticated fiction. Right? You don't have to believe any of that I am going to say, and that any of that's in those 4 books. It's just fairy tale. But if we can extend that to these things, it's good. So for at least that sake, we have to have a supersymmetry in those theories. If we can make the simplifications, so these many diagrams will be. All you have to know is only to like tree level. You can calculate any of these things. You can skew and you can calculate one and then you can calculate anything else using these theories. So like 100-page calculation is just one line calculation in this. But in superangles theory, right? So 10 gluons in superangles theory interacting at the tree level, they can calculate this in one page. And no computer on earth with any amount of computing power can do this for QCD. Right? So that's why it's surprising and amazing, although it has nothing to do with reality. Right? So that's the thing. So our intention is not to be happy with what we have. How do we extend these ideas to something real? Right? Like, can we answer the professor? Can we calculate this to two loop level using any of our techniques? If not, we have failed. Okay, so and as of now we cannot. Right? So as of now, with any of these techniques, we cannot calculate this process to
I think that the moral of a theory is to take numbers.
Sure.
If you don't make numbers from the theory, and so, let's say, numbers is that you are going to measure.
Yes.
So, let's say, this is your course is very important for us because you are going to show the methods to make numbers
Exactly.
from a given theory.
Exactly. So yes, that's correct. So in quantum field theory course, what you learn is renormalization, regularizations, and this kind of things. But how do you verify any of that is, at the end of the day, the only method to verify is to calculate the cross sections. That's how you verify whether the theory is right or wrong, right? So this course is about calculating those things. Maybe in the beginning I will calculate for some of the simple things, because there is no point in calculating n-gluon process recursion relations using BCFW relation n equal to 4 super Young-Gibbs theory when we haven't calculated the Dirac process, right? So it's nothing like I have to finish everything in one semester or in one lecture or anything. I am going to give these lectures whenever I get the time in between. The idea, totally what I want to introduce, the only thing I want to introduce is there is a new ongoing revolution in theoretical physics. May not be related to reality, but in theory, in theoretical physics, there is an ongoing revolution in the last 10-15 years, right? And that hasn't reached Brazil yet. And usually it's the young people who start this kind of new things. So if you are interested, this is a good direction to think about, right? So that's all I want to know. And I'm not selling anything here. You don't have to believe supersymmetry. Yes, it's not experimentally verified. You don't have to believe super angles or supergravity or anything for that matter, right? Some people say I don't believe in gravity. There's one episode of Friends. I don't know which episode. Phoebe, I think she tells, I don't believe in it's a theory, gravity is a theory. Yeah. So you don't have to believe in anything, right? So go find that episode where she says, oh, gravity is only a theory. Tell that to a person who is jumping from the 10th floor of the building, right? So anyway, these are the processes. I will try to calculate these processes at least to tree level, right? So just to show how the scattering amplitudes work, right? Moral of the story, at the end of the day, if you have any field theory, there is only one method to verify, get the numbers out of that is using amplitude and cross section, right? And in experiment we did it. And some of the processes in the Bragg-Wheeler thing that the professor was mentioning, we have numbers theoretically, but we don't have the numbers in experiment to match those things. So that's the problem, right? And don't think supersymmetry doesn't produce any numbers. They produce lots of numbers, and any number you want. But experiments, we don't have anything in experiment to match with those things, right? So this is. And another thing is, another selling point why we have to consider supersymmetric theories is because it makes things simple. This kind of things which is impossible for supercomputers, all the supercomputers in the world, can be calculated in one page if there is supersymmetry. Right? So in that case, let's use this and understand something. Later, let's strip away supersymmetry and then try to come back and do the real bread and butter, Arhosh-Fejar processes, right? So to do the things. Yes. So this is, and also, okay. So later, I will list all the methods for calculating the amplitudes, right? So if you took any quantum field theory course, you will learn perhaps one method of calculating these things using either using the trace technique or spinor helicity formalism, something like this. Have you learned any of the methods to calculate this? There are like standard textbook method is to calculate using the trace or spinor helicity. Are you familiar with it? No, right? So I am going to do that for you. So either one or two methods in the standard quantum field theory textbooks. I am going to list all the methods there is to calculate the scattering amplitudes, right? Okay. So, any questions so far? Any questions so far? Yes, yes.
I don't understand. You said you can calculate these things with
That's correct, yes.
why you can? This is very difficult. Why you can't very to calculate? But there is easier.
Yes.
But why you can't calculate those ones that should that easier?
Yes. Good question. Did you understand this? This is, gluons are much more complicated than electrons and photons, right? Gluons can self-interact, and they have colors and so many things, right? So, whereas these things are very simple. Why do I say we calculate? Oh, when I said that we can calculate these things, it's like a cheating in the sense, it's not like you calculate this n-gluon process in QCD, but there's an equivalent of n-gluon process in super Yang-Mills theory. You can calculate that, right? So, not the real gluons, the gluons of the super Yang-Mills theory, you can calculate these things in those. In QCD we have quarks. There in super Yang-Mills everything is like massless. Everything travels at the speed of light. Everything is gluon. So in super Yang-Mills, this is just Yang-Mills theory, it's QCD. There are gluons also in that. Only in those you can calculate, right? But it's a good question. We can also have a supersymmetric version of QED, right? So we should be able to calculate these things in those, right? That's a good question. I haven't seen any papers or any textbooks, anybody talking about these things. Maybe I just missed those, right? But it's a good question. That's an interesting problem to work on, right? In a supersymmetric QED, can you use these new techniques to calculate these processes? Although this is going to be like a supersymmetric version of this. Can we calculate an equivalent process? That's a good question. Because everybody talks only about gluons. Why is that the case? Because that's what they want experimentally, right? So all the hadron colliders, LHC and other things, you are not colliding electron-electron in the LHC. You are not doing electron-photon. What you are colliding is two protons. When you collide two protons, you are basically colliding quarks and gluons, right? And they produce this. So that's why everybody is concerned about those methods, so that these things, maybe we can strip away supersymmetry and use them to calculate the regular QCD processes. That's the motivation. So, and not this one. These are like large electron-positron collider at Fermilab. They will be doing like electron-positron, this kind of things, right? Yeah, for that processes this will be interesting. But now that's not, it's done, it's over. So people are just worrying about whatever is currently in experiment, which is LHC, and then something called, I will give you the list of things again. In Brookhaven National Laboratory, there is something called RHIC, like relativistic heavy ion collision collider. So they have like, they take heavy ions, like iron, this kind of ions, and then like collide them and create quark-gluon plasma. So basically you are creating the same energy, same environment, what was just a few seconds after the Big Bang, right? So that kind of environment. For those processes, only gluons are important, not electrons. That's why nobody, but it's a very good question, right? It's a very good question. Can we calculate these processes in supersymmetric version using any of the techniques? I don't know it. If we can do that, that will be a very good paper. Okay, so Journal of High Energy Physics. Okay, so this is any other questions so far?
I have a
Please.
question. May I ask you, is it possible to have a QED scattering all this? If you don't have the electric charge, if the electric charge is zero?
Yes, there is something called scalar QED.
QED.
QED with scalar particles, meaning without spin. Without spin, you can have like a spinless electron. You can take away the spin from all of these things. You can write down. You can still do a QED with that. Can you do QED without the charge? There is charge in those. Did you guys understand the question? If there is no electric charge here, can we do QED? It's quantum electrodynamics. The electrode has the charge, right? So you have to have a charge. But spin is not necessary. We can have spinless QED. It's called scalar QED. Yes. But it's not a physical thing. But mathematically, you can do and calculate the cross-sections everything. In fact, many of the standard textbooks, they do this in the first chapter. They do scalar QED because doing these processes. In fact, Hansen and Martin, I think they do this for these processes, at least some of these processes, without assuming any spin for the electron. As if electron has spin 0. Can you do these processes? Yes. Is this real? No. But mathematically you can do it. Yes. Yes.
Yeah, and my second question for you, is it for your mind, for your opinion, it's possible to have one scattering that it doesn't happen at 3 levels, but just starts at one loop?
That's a good question. Do you know any scattering which happens only at one loop but not 3 level? Oh. That's a good question. I don't know the answer. I should have a new thing here which has for the questions which I don't know any answer, right? So maybe a bottle of cachaça. so that would be, yeah, I don't know anything. Is there any process which starts only at the one loop? Does it happen at the 3 level?
Make the photon scattering. Photon, it starts just one loop.
Yes.
Perhaps you put right off and people see.
So you had something like this, right?
Photon scattering. So this scattering doesn't happen
At the
at one loop. At
3 level.
3 level.
Yes.
It started one loop. It is a question because this is that sometimes I don't like this.
This is bothering the professor. Okay, so I'll make a T-shirt for you with that thing.
In my opinion,
Yes.
in my opinion, the biggest problem, I don't believe in Higgs.
Sure, it's correct. Yes.
I think that the Higgs is something wrong.
Why?
People think wrong. Why? Good question. Because the Higgs doesn't interact
It does interact with itself.
at 3 level. Let's say you get the Higgs just once indirectly. Photon interaction. Yeah, it is in loop. The Higgs is. If you have I'm interacting with the Higgs with some part at 3 level. I understand that you have measured the Higgs. So, my opinion is that amplitudes are a big question for this amplitude subject. Is that if you can have, it is valid to make scattering that doesn't happen at 3 levels.